Hi, I'm Brian Dickinson, and this Trading Byte shows you how to add operations to UVM classes using the visitor design pattern. So if we want to add a new method to all or most of our classes in a UVM test environment, then we have a few options. Obviously, we could edit every class to add the method, but that is a lot of copy-paste to edit every class, and we don't really want to be editing the source code of reusable UVCs. The standard option would be to declare the method in a subclass and use type overrides with a factory. However, again, to affect every class would require a huge number of subclasses and type overrides, so this is not really practical. But this is a standard object-oriented design problem with a standard solution called the visitor design pattern, which is implemented in UVM 1.2 onwards. In the visitor design pattern, you declare the method in a single class, then traverse the hierarchy to visit every component and execute the method as part of the visit. As an example, UVM 1.2 onwards has a built-in visitor which checks the instance name of every component. Now, the instance name can be any string, so the value is not checked by the compiler. However, some characters may break UVM functionality if used in an instance name. For example, non-printing characters may break topology prints, and the use of the dot hierarchy delimiter in a name will break configuration settings. So the name check visitor visits every component in the hierarchy during end of elaboration and checks the instance name against a regular expression to enforce a naming rule set. If I try to name my test bench TB++, the visitor generates a warning that the name violates the rule set. To understand the visitor design pattern, let's examine the implementation and terminology. The visitor is a class which defines the operation method. The structure is the data to be visited, e.g. the component hierarchy of a test bench. An individual component in the structure is called a node. The adapter traverses the structure to visit every node and execute the visitor method. Finally, the context links the visitor, structure, and adapter and defines from where and when the structure traversal starts. So here is my visitor class called name_visitor. We extend from UVM_visitor, which is type parameterized for a UVM component structure by default. In the unlikely event the structure is of a different type, for example pure data, you would have to explicitly type parameterize the visitor. The visitor is a data item, so we have a standard UVM data constructor with a single name argument. The operation must be defined in the void function visit. Each node in the structure we are traversing is passed into visit via the argument node. The node type must match the type parameter of the visitor. Here we will simply print the full name of the node. The visitor can optionally have begin and end operations. Void function begin v is executed before the first node is visited, and end v is executed after the last node is visited. Here we have a local property count, which we assign to 0 in begin v, increment in visit, and print in end v to report the total number of nodes visited. We don't have to define our own adapter. There are 3 built-in adapters for traversing a component hierarchy in different ways. If we use the top-down adapter from test, we traverse test, then TB, then UVC1, UVC1 agent, and then UVC1 sequencer driver and monitor, then UVC2, its agent, and UVC2 sequencer driver and monitor. The bottom-up adapter will start at the sequencer driver and monitor of UVC1, then UVC1 agent and UVC1 itself, then the sequencer, driver and monitor of UVC2, followed by UVC2 agent, UVC2 itself, then TB and test. The bi-level adapter visits all components in a level before descending. So this would traverse test, TB, UVC1, UVC2, UVC1 agent, UVC2 agent, and then UVC1 sequencer, driver and monitor, finally UVC2 sequencer, driver and monitor. We could define our own adapter, but the built-in options are usually sufficient. Let's put this all together in the context. In the end of elaboration phase method of the test class, we declare handles for our user-defined name visitor, for the built-in top adapter, and also a built-in proxy to navigate the structure. More on proxies and adapters on the next slide. We construct the visitor, adapter, and proxy instances. Then we execute the accept method of the adapter. We pass in the starting point for the structure using keyword this, so we start in the test class. Next argument is the visitor instance, and final argument is the proxy. So the adapter will traverse every component under test, top down, to execute the visit method of the name visitor. A quick word about adapters and proxies. The proxy must extract the direct subcomponents of the current node of the structure in the method getImmediateChildren. For a component hierarchy, this simply calls getChildren to push the subcomponents into the queue children. The adapter then recursively calls its accept method to execute the visitor visit function and traverse the structure using the queue of subcomponents from the proxy. For a top-down traversal, this is easy. We just recursively call accept on every component in the queue. Bottom-up and bi-level traversal is a bit more complicated. Take a look at the UVM traversal source file to see these implementations. If we use built-in proxies, we don't have to worry about the implementation. Let's see the example in simulation. Here is my visitor class. We are using the beginV and endV methods to track the number of nodes visited, and we simply report the node name for each visit. Here is the context setup in the end of elaboration phase method of my base test, just as we saw on the slide. Handles for visitor, adapter, and proxy. Construct the instances. We do not use factory create because of the strong type dependencies between visitor, adapter, and proxy. Then trigger the visitor traversal by calling the adapter accept method with the structure, visitor, and proxy references. Finally, I print the topology to check against the visit reports. Let's run a simulation. Here is my topology, a simple single UVC under a test bench and test class. Here are the top-down visit reports. We can see the test, TB, UVC, agent, sequencer, driver, and monitor components are all visited. Note that in UVM, TLM connections are inherited from UVM component and so count as components for the traversal. So we see the TLM connections under the driver and all the TLM connections under the sequencer. So every component is visited. The endV method report tells us we've visited 22 nodes in total. Now you may want to execute different operations depending on which node you are visiting, or only execute operations for certain nodes, for example, only for driver components. The options for filtering nodes are a bit limited. We can detect TLM nodes by casting to a handle of type UVM port component base. Please search for the training byte Extracting and Debugging TLM Connections on support.cadence.com for more information. We could also filter by instance name using a regular expression. Please search for regular expressions in configurations for more information. We could detect monitor nodes by typecasting to a handle of UVM monitor, but we couldn't detect driver nodes by typecasting to UVM driver. Drivers are type parameterized, which creates a specialization of the UVM driver template, and so is a different type. Detecting drivers with a cast requires knowledge of the type parameterization, and so your visitor becomes specific to a certain set of UVCs, and this affects reusability. Let's see some filtering in simulation. So we detect TLM nodes with a cast to a UVM port component base handle. We try detecting driver nodes with a cast to a UVM driver handle. We have a regular expression to detect an instance name containing characters D, R, any number of characters, then V. Remember, UVM rematch returns 0 if a match is found. Sequencer nodes can be detected with casting, as there is a UVM sequencer base type. Finally, all other nodes are simply printed. Run this in simulation. Traversal is top-down. The driver node is detected by name. The attempted cast to UVM driver has a higher priority, but didn't work as the driver is type parameterized. TLM nodes are detected. The sequencer node is detected by the cast. Note the sequencer analysis and response FIFOs are detected as components, not TLM nodes, although their connections are reported as TLM nodes. So that's the visitor design pattern in UVM. I hope you found it useful.